Good afternoon. Am I audible?
Yes, sir. Yes, sir. Yes, sir, I have a question, sir. Hello?
Yeah, go ahead.
So does the time reversal operator represent the observable, sir?
What time?
Reversal operator
Ah,
representing observable.
um, yeah, so that is basically a kind of a symmetry operation, right? So time
Yes, sir.
reversal is a symmetry operation.
Like parity.
Yeah, yeah. It will be like parity.
But sir, like time linear. So like the observables are their representations operator are linear, but time reversal operator is anti-linear. That's why I'm asking.
But actually, the transformations are not same as the observables in general. For example, you can talk about a rotation operator. Rotation operator is not any physical observable. It is only a transformation.
Yes, sir.
So it is, in that sense, it doesn't have to be on the same footing as the physical observables.
Yes, sir. And sir, I was watching this your lecture on CSCO. There you
Mm.
have mentioned that if two Hermitian operators commute, then it is not guaranteed that every eigenvector of A would be the eigenvector of B.
Mm.
But we can say that there exists a common basis, orthonormal basis,
Mm.
that is whose vectors are common joint eigenvectors of both A and B.
Mm.
But sir, I was reading Zetili book. There, they have written that every eigenvector of A is an eigenvector of B.
Yeah, but that is not correct. I have given also an example in that
Yes, sir.
lecture
Yes,
why
sir.
that is not correct.
Yes, but sir, can I show you the book?
Yeah, so the point is maybe everything that we see in the book is not correct.
Yes, sir.
Don't have to worry about that. But if you understood what is correct, that is enough.
Okay, sir. Okay, sir. And sir, from the last class, I have a doubt.
Mm.
Sir, in the last class, 1 minute, there was a like the for a pure state, psi AB is summation I equal to 1 to D, summation j
Mm.
equal to 1 to Cij, ket Ia, direct product ket JB. So
Mm.
Cij is a Hermitian matrix. Why is it Hermitian? The C operator, CC matrix is a Hermitian matrix. Why it is Hermitian?
Clear, right?
Yes, sir, that one.
Uh, so I think I also showed this later sometime.
No, sir, like you have used the property of the Hermitian matrix.
Uh,
You
okay,
have
so what?
mentioned that lambda I are real, like,
Correct.
but because of Cij is Hermitian. But why C is Hermitian?
So what basically that means is that your Cij J is equal to Cji star. Correct?
Yes, sir, yes, sir.
This is what we should have. So now if so this is what is the meaning of that distribution.
Yes, sir. But I'm saying why I'm asking why C is a Hermitian matrix.
Okay, so I'll try to present an argument for that. Let us try this. So we have something like psi AB equal to sum over I 1 to B, sum over J is equal to 1 to B. Okay. Then, supposing if I ask what is rho AB corresponding to this, rho AB corresponding to this is psi AB, psi AB. That is our rho AB. So that is equal to, now I will have sum over I K, and then I will have sum over K L. Okay, so I will have Ej and CKL star of IA cross JB, and then I will have KA product LB, something like that. So we can probably write this in some shorthand notation like this: IJKL, IJKL, CIJCKL star. Let's write this as IAJB, KAL, IAJB, KAL. Now it is like you can say that this rho AB's IJKL component. IJKL component is CIJCKL star. That is, if you are imagining this as a matrix, then IJKL component is IJKL component is this one. So it is like what we are writing. Yeah, CIJCKL. So this is like in the previous discussion, we had this, to recall that we had this kind of a notation. So here you see we have this rho 0, 0 and rho 0, 0 tilde. So this I would write it as rho 0, 0, 0. So that is the meaning of that. Okay, so in that notation, I would say that this is like rho AB of IJ, rho AB tilde of A. So that is given by this. Now you know that so now you know that this has to be Hermitian. Rho has to be Hermitian, and probably that is what gives us a requirement that the Cij matrix has to be Hermitian.
Okay, sir. Okay, sir.
You can try along these lines.
Okay, sir.
Yeah.
Sir, one more question, sir, in the last class. So, in the proof of the Smith decomposition, we have like there was a unitary operator Like,
Mm.
so UIK,
Mm.
UKL dagger, UKJ dagger. So shouldn't that be identity, sir?
Uh, UIK, UKJ dagger.
Yes, sir. We can put that equal to identity. No, sir. Yes.
UK, yeah. So I cannot. Uh, I think your question is with respect to. So you know that U dagger is identity, and hence U IK UKJ sum over K will be equal to UU dagger of IK. But since that is identity, this can be written as UU dagger of II into delta I. Correct?
Yes, sir. Yes.
Yeah. So this is correct. So here, if I take this summation over K and then just look at this alone, then I will get that. But then the summation over K is not for this alone. This is multiplied with lambda K, and this I and J are summed over. So here what we are doing is we will not be able to isolate this summation over K with UIK, UKJ dagger alone.
Okay, sir.
And that is why we are defining this basic.
Yes, sir. And sir, like K is a dummy variable, no dummy index.
Yeah.
So dummy index, can that be three? Like, can we have three dummy index in an equation, like in an expression?
No, here K is dummy only because in the final expression K equal to 1 to D is there, right? Summation
But there are
there.
three Ks.
Yeah, that is okay. That is you mean lambda K, psi K, phi K. That is what we are
Yes,
telling.
yes,
Right?
sir.
That's okay.
But like, but dummy index can maximum be two, no, sir?
No. What I'm saying is that here I'm not using that index notation at all. I'm just simply using the summation index, right?
Yes, sir.
So this is so basically this psi K, phi K is the index of the same state, a product state.
Okay, sir.
So that is how we have to understand. Yeah.
Okay, sir. Thank you, sir.
Sir, here how you wrote that IK as II, sir?
Because this is identity, no? Identity will be simply delta Ij, right? So
Yeah.
Ik element, only when k equal to I, it will be there, otherwise it will be 0. Okay, so since it is identity, if I equal to k, it will be surviving, otherwise it will be 0.
But why you writing it, sir? We can just like that write U dagger IK. So why you are trying to put on delta function and make it more complicated? Is there any particular reason for writing in this manner?
No, this is the correct way to write, because if you say UU dagger is equal, for example, let's say that I have a matrix A and another matrix B. The product of these two matrices is I, let us say identity. Then how do I write AB of IJ? That is, what is the ijth element of AB? Ijth element of AB has to be only I element, no, that 1, 1, 2, 2, 3, 3, only they will be there. So we should write that as AB of II into delta Ij. Now, since this I is repeated, so you can say, suppose I is equal to 1, this will be AB 1, 1, and your J should be equal to 1. Only then that element will be non-zero. If I equal to 2, 2, 2, and J should be equal to 2, only then it will be there. If J is different from 2 or whatever value of I, then it will be 0.
So this is valid for any diagonal matrix. No, so means if AB equals to identity, then AB IA equals to 1. No, sir?
Yeah, if it is identity, then it is simply 1. Okay, so this is basically equal to delta Ij. Okay, but if it is not identity, if it is diagonal, let's say, yeah, that is correct. If it is diagonal, let's say this is, let's say some D1, D2, etc. It can be like that. Then you will say instead of this, EI delta I. Then it is not equal to delta I. It's just a notation. But this is the correct way to write it. Okay. So let us look at mixed states. We have been talking about pure states so far. So let us turn to mixed states. In one of our previous classes, we have talked about don't know if I, oh. Okay, in one of our previous classes, we talked about pure states and what can you do with the pure states if they are entangled states, and entanglement can be used as a resource for achieving something which cannot otherwise be achieved classically. Namely, we discussed super dense coding, we discussed what is called the teleportation and this kind of protocols in the last class. So today we talk about mixed states. Okay, so we talked so far about the pure states, now mixed states. So we have talked about mixed states in one of our earlier classes with respect to Qubit. So mixed states are represented by density matrices. Okay, so a density operator or a matrix. So let us look at a simple qubit case. Okay, for a qubit system, now density matrix is, let's say, rho is a 2 by 2 complex matrix. 2 by 2 complex matrix. Now we know that if you consider a vector space of set of all 2 by 2 complex matrices, then V is a vector space. V is a 4-dimensional vector space because you require 4 complex numbers. 4-dimensional vector. Now there is an interesting basis for this 4-dimensional vector space. So one of the bases, basis is not unique, but one of the bases that for this 4-dimensional vector space is given by this. So you have 1, 0, 0, 1, this is identity, and 0, 1, 1, 0, 0 minus I 0, and 1, 0, 0 minus. So if you can recall, this is basically identity. Then you have sigma x, sigma y, and sigma z. These are Pauli spin matrices. So these are called Pauli spin matrices. Pauli matrices. So identity and three Pauli matrices will become a basis for the four-dimensional complex vector space of 2 by 2 matrices. That means if the density matrix is 2 by 2 complex matrix, then it can be expanded in terms of this basis. So we can write, the rho can be written as some coefficient. Okay, so let me call this as some coefficient x naught into identity plus x1 into sigma x plus x2 into sigma y plus x3 into sigma. It is possible to write like this. Now notice that note that trace of sigma I is equal to 0 for I is equal to x comma y comma z. All the sigma matrices are traceless matrices. So the trace comes only from the identity. Okay? And trace of identity is actually equal to 2. Okay, so in our one of the requirement for any 2 by 2 matrix, okay, for rho to be a density matrix, we have to have trace of rho should be equal to 1. That is the property that we have talked about. That means, so this implies our x naught has to be equal to half. Okay, then only the trace becomes 1. Other three matrices are traceless matrices. Okay. So now what we can do is we can now say that we will write this rho. Okay, so let us write this rho as half identity plus a vector x dot the vector sigma. Okay, what is x? X vector? X vector is x1, x2, x3. And sigma vector is sigma x, sigma y, sigma z. Okay, so like that we can define. Now, of course, we require to ask what should be this x. Okay, so what is the one more, since sigmas are Hermitian operators, rho is Hermitian. Okay? So rho dagger is same as rho, since sigma I dagger is same as sigma I for all I. So x, y. So hermiticity property, there is no problem.
Sir, there is a rule that density matrix should be also Hermitian, isn't it, sir?
Yes, it is. That is what I am saying. It is Hermitian because sigmas are Hermitian. This is Hermitian. So that rule is satisfied. So this way of writing trace rho is equal to 1. That is also satisfied. And this is also satisfied.
Sir, why like the bracket, like half bracket I x dot sigma, because x is like x1,
Yeah,
x2, x3.
yeah.
So
So
the half will multiply. No?
yeah, that is multiplied. So it doesn't matter. So I can simply call this as by 2 by 2 by 2. In hindsight, that I'm going to take this is equal to half here. Then I will simply pull out half and call the remaining ones as x1, x2, x3. Anyway, x1, x2, x3 we are going to determine, so there is no problem if I do like that. Okay, so now what is the other condition? The other condition is that rho has to be positive. Rho has to be This is the main condition. Rho has to be positive. That means there are many definitions of this, many equivalent definitions of this positive. So in general, a matrix is said to be positive if so a matrix is positive if suppose a matrix M is said to be positive if X transpose MX is greater than or equal to 0 for all X, for all vectors X. So that means this is basically called a bilinear form. So you have a matrix here, and this is like a column vector, and this is like a row vector, a quadratic form. So you have elements like this, then you have elements like this, and you have elements like this. Now this quantity should be greater than or equal to 0 for all X. So in some sense, this is like an expectation value. Expectation value of M is positive with every state. Then it is a positive operator or positive matrix. Or equivalently, eigenvalues of M are non-negative. They can be 0 or they can be positive. Eigenvalues of M are non-negative. Now there's also another equivalent way of saying this. Suppose you have your M like this. So let's say this is M11, M12, and so on. M21, M22, and so on. M31, M32. So let's say that you have a matrix like this. Now you can say that, so you consider a 1 by 1 block of this, that is M11. Now this has to be positive. Now you take a 2 by 2 block of this, and determinant of this has to be positive. Now take a 3 by 3 block of it, and determinant of this is positive. So let us call this delta 1, delta 2, delta 3, etc., delta n. This is determinant of 1 by 1 matrix, 1 by 1 block, and this is determinant of 2 by 2 block, and this is determinant of 3 by 3 block, and this is determinant of the whole matrix, determinant of n. Now a matrix is positive means that all are positive. These are all positive. All these determinants of these blocks are positive. So these are equivalent definitions of showing that a given matrix is positive. Now we are asking a question that so for what values of X is rho positive? So we ask that question. Now we have to ask question, what is rho? So rho is equal to half identity plus X dot sigma. So if I span that one, so let's say I have half, and this is 1001 plus, so let's say x1 sigma x and x2 sigma y like that. So this is x3, x1 minus ix2, x1 plus ix2, minus x. So as a result, sorry, we have a matrix which is 1 plus x3 by 2, x1 minus ix2 by 2, x1 plus ix2 by 2. So this is the matrix row. Now we have to see one of the easiest thing to verify that it is positive. So I will use this one. So this 1 by 1 block. So that means 1 plus x3 by 2 has to be greater than 0. That means 1 plus x3 is greater than 0. That implies x3 is greater than minus 1. Okay, so this is the condition that I am getting. And now let us look at the determinant of the full thing. That is 1 plus x3 by 2 into, this is what I have shown here is delta 1. Okay, that is equal to 0. Now I am going to take delta 2. 1 minus x3 by 2 minus x1 minus ix2 by 2 into x1 plus ix2 by 2, and this has to be greater than 0. So greater than or equal to 0. So that implies we have this 4 anyway. We don't have to worry because that you take the left side, right side, it will become 0. So I have 1 minus x3 square minus x1 square minus x2 square greater than or equal to. Or in other words, this implies x1 square plus x2 square plus x3 square less than or equal to 1. Okay. So this is basically the condition. Okay, so that implies the condition seems to be that the modulus value of x1 or modulus value of this vector x has to be less than or equal. Okay. So now you have an interesting interpretation. So that means you have a general density matrix of a qubit is described as that rho is equal to half I plus x vector dot sigma vector, where x vector has a magnitude that is less than or equal to 0. The magnitude of this x vector has to be less than or equal to 0. The magnitude of x vector, the lower limit of the magnitude of the x vector has to be actually greater than 0. So this is 0 less than or equal to x less than or equal to 1. So this is the complete description of a general mixed state, a general density matrix, which is basically a mixed state. The general qubit mixed state is written by a density matrix. Now let us try to go back to our block sphere. So recall that we had block sphere where now we can interpret
Sir,
interpret x as a vector as a vector uh, in or from the center of the block sphere, from the center of the
sir,
yeah.
how did you fix the lower limit of modulus x, sir, less than, like 0?
Modulus of any vector has to be greater than or equal to 0. It will be 0 if the vector is 0, otherwise it has to be greater than 0. Okay, that is related to length of the vector.
Like a norm of vector.
Yeah. So now you can see that. So one thing that. So why am I interpreting it like this? So suppose you take rho square. So rho square is equal to 1 minus x3 by 2 x1 minus x2 x1 minus ix2 by 2 x1 plus ix2 by 2 1 minus this is 1 plus this is 1 minus x3 by 2, and then you multiply this with itself 1 plus x3 by 2 x1 minus ix2 by 2 x1 plus ix2 by 2 1 minus x3. Okay, so now I want to ask what is the trace of rho square. And trace of rho square, it is sufficient if I calculate 1 1 and so that is basically rho square of 1 1 plus rho square of 2. Right. So 1 1 element is 1 plus x3 the whole square by 4 plus x1 square plus x2 square divided by 4. That is 1 1 element. And 4 4 2 2 element is x1 square plus x2 square divided by 4 plus 1 minus x3 the whole square divided by 4. So this is your trace of x square. Okay, so now if you do this, so this is 1 by 4 into you have 1 plus 2x3 plus x1 square plus x2 square plus x3 square plus here you have x1 square plus x2 square plus x3 square will be there, so that will be 2 2 2 here. Okay, and plus 1 will be there, and minus 2x3 will be. So this minus 2x3 and this plus 2x3 will cancel. So I have 1 by 4 into okay, there is a 2 common in every term, so I pull that 2 out and then write this as 1 plus x1 square plus x2 square plus x3 square. That is equal to half. Outside 2 by 4 is half. So that is equal to half into 1 plus modulus of x square. Okay. Now, if we demand that trace rho square is equal to 1, that implies half into 1 plus the magnitude of this vector square is equal to 1. That implies modulus of that vector is equal to 1. Okay. So now you can see that in general, for rho to be a density matrix, recall when I say rho has this expression half I plus x dot sigma. Okay, so for a row like this to be a density matrix, modulus of x has to be less than or equal to 1. And if modulus of x is equal to 1, then rho is a pure state. As we have discussed earlier, both pure states and mixed states can be represented by density matrices. If x is equal to 1, then rho is a pure state. And if x is less than 1, then rho is a mixed state. Because if x is less than 1, then trace of rho square is less than 1. Then rho is a mixed state. Because of this, we can imagine the following situation, that we have a block sphere, and starting from the origin of the sphere, center of the sphere, have a vector. Okay, so now this vector is what I'm calling it as x vector. Now this x vector has got components x1, x2, x3. Remember, this is a unit sphere. It means it has a radius 1. Now, if the tip of this vector is reaching to the surface, that means your magnitude of this vector is equal to 1. Implies the tip of the vector is on the surface. And we have already seen that in block sphere, all pure states are points on the surface of a block sphere. So therefore, we have a geometrical structure or the state space here, that all points on the surface of the block sphere which you can actually draw a parallel to Poincare sphere in polarization. The concept is same. A block sphere are pure states. Pure states are in the language of optics called completely polarized states. Okay. And points in the interior of the sphere, points in the interior of the sphere are mixed states. In the language of polarization, they are called partially polarized states. Partially polarized. And the origin or the center of the sphere represents maximally mixed in the language of polarization. That is what represents an unpolarized state. Okay, so this interpretation will tell us that you can talk about a geometrical structure for the state space. So the state space, if you are talking about qubit state space, okay, and previously we talked about pure states. When I consider only pure states belong to what is called a Hilbert space, belongs to something called a Hilbert space. It is a two-dimensional complex Hilbert space. But there are no mixed states in this. But if you include mixed states, okay, now you can define something called um, set of all bounded linear operators, set of all bounded linear operators on H. Okay, so this is what you will have as the state space. That means these are all set of all bounded linear operators on H will become the state space of the qubit. So this includes both pure and mixed states. Okay, so this is about pure states and mixed states. So what is the max? So the maximally mixed state, so rho is equal to maximally mixed state corresponds to the center. Center means x1, x2, x3 are 0, 0, 0. So essentially rho is equal to half identity is maximally mixed state. So you can see that when we talked about entanglement of pure states, when we took partial trace, we have got maximally mixed state. That is, we got half identity for both subsystem A and subsystem B. Okay, so this is maximally mixed state. Okay, so now we can go back and then ask, how do we talk about mixed states? Okay, so let's now look at mixed states of two qubit system. Mixed states yeah. Hmm. Yeah, I think we have concluded that last time that suppose you have psi AB, a pure state, Okay, so larger the entanglement, then your rho A, which is equal to trace over B of psi AB, psi AB, psi AB, larger the mixing here. So if you have highest entanglement, that is if your state is maximally entangled, then this will be maximally mixed. So this is what we have used, and then we defined what is called that von Neumann entropy to get as a measure of. So von Neumann entropy essentially measures the mixture of rho A, how mixed is this marginal state. Now, if it is largely mixed, that means it is the pure composite state is maximally entangled. So that we have already mentioned last time.
So qubit state space is also two-dimensional.
Huh?
Qubit state space is also two-dimensional.
Yeah, so normally when you say that, when we talk about qubit and we talk about Hilbert space, it is only considered as this Hilbert space. But when you consider all the state space, essentially when you consider it a set of all boundary linear operators, then that is actually four-dimensional. But in the literature, we don't talk about that. We only talk about Hilbert space and then operators on the Hilbert space. So what is the state space dimension of qubit if somebody is asking? Then I think we should say it is two-dimensional, but that is only referring to this Hilbert space.
So because it is divided by 2, identity divided by 2, 2 is a dimension, that's why I asked you. Because operators are 4 dimensional, but
correct.
They're 2 dimensional.
Okay. Okay, so yeah, so that is fine. Maybe I'll come back to that later. So now mixed states of a 2-qubit system, and 2-qubit system, so the dimension of the Hilbert space, the dimension of the Hilbert space is basically a tensor product of these individual Hilbert spaces HA and HE. So it is equal to 4. It's a 4-dimensional vector space. So the density matrix of a 2-qubit system is a 4x4 complex matrix. Now, if you consider a V, which is a set of all 4x4 complex matrices. Okay, set of all 4x4 complex matrices, and it's a vector space. So it is a 16-dimensional vector space, because there are 16 elements for 4x4. 16-dimensional vector space. Now, one can talk about a basis of this vector space. So the basis is not very difficult to figure out. Now, the basis is something like this. You have an identity. This will be a 4x4 identity. Then you have a 2x. So let me call this as I4 to say that it is a 4x4 identity. Then you can have an I2 cross sigma x and I2 product sigma y, and I2 is 2x2 identity, sigma z. So these are 3 matrices, And then you can have sigma x product I2, sigma y product I2, and sigma z product I2. So you can see 1, 2, 3, 4, 5, 6, 7. Okay. 7 are there. And then you can have matrices of this type, that is sigma x product sigma x, sigma x product sigma y, sigma x product sigma z. Then we have sigma y product sigma x, sigma y product sigma y, sigma y product sigma z, and sigma z product sigma x, sigma z product sigma y, and sigma z product sigma. Now you can see that we have 16 matrices. So this is a basis. Okay. Now I can write it in the following fashion. So a general, again you notice that the trace, okay, so a general 4 cross 4 complex matrix can be expressed as a linear combination of the above basis elements. Okay, above basis elements. Now again, if you see the trace of all these matrices is 0 except identity, 4-dimensional identity, and hence the trace of rho is given by the identity only. And for example, if you demand that trace of I should be equal, trace of rho is equal to 1 implies the coefficient of I4 should be 1 by 4. So we can write down a general 2-qubit density matrix. Density matrix can be written as a general 2-qubit density matrix can be written as rho AB is equal to 1/4 of I4 plus. Now let's try to write this in the following fashion. Sum over I is equal to 1 to 3. So let's say some Ri into I2 cross sigma I. Ri are the coefficients. I2 cross sigma I are the vectors. Plus sum over I is equal to 1 to 3. Some Si into sigma I cross product identity. That is, in the first summation, I have taken care of all these 3. The second summation, I have taken care of all these 3 matrices. Then we have plus summation over I is equal to 1 to 3. Summation over j is equal to 1 to 3. and I have some Tij into sigma I product sigma. So in this term, I have taken care of all these 9 matrices. Okay. So now remember, this is a bit more complicated than what we had earlier. And you can see that this particular matrix is the most general matrix of a 2-qubit mixed state.
Sir, here, what is this Ri, Si, and Tij? Sir, what are those?
So these are coefficients like x1, x2, x3 in the previous case. Okay, so these Ri, Si, and Tij are coefficients.
But Tij is a matrix, isn't it, sir? Or it's a coefficient?
Yeah, there are 9 coefficients. So Tij, there are 9 coefficients. Yeah. Yeah, go ahead. So if we have yeah, tell me. Yeah. Hmm. Um, so you're asking this question with respect to qubit. You could have asked there also, right? Yeah. So the point is that if you have a vector space of complex matrices, okay, we have vector space of complex matrices. You could have used this kind of a basis: 1 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So I used this basis. Okay, this is another basis, right? Now the point is, if this basis, if you use, then your coefficients have to be complex numbers. But if you use this basis, your coefficients, you can actually get a very complex matrix with the real coefficients, because there is one complex matrix sitting here. Yeah, yeah. Yeah, correct, correct. So it is because you can actually use the real coefficients. If you take these complex matrices, you can use real coefficients. Okay, now you can, it is easy to understand. So this Ri is a vector, Si is a vector, Tij is like a matrix. Okay, now I2 cross sigma I is like just the system B, or sigma I cross I2 is like system A. So suppose if you are thinking that, okay, second system is, you are not doing anything on that, you are only considering one of the system. Our previous analysis will tell you that this R vector should be less than or equal to 1, and this S vector also has to be less than or equal to 1. Okay, because they are like a single qubit system. Okay, now uh, suppose you have a state. Okay, if let's say Tij is equal to 0 for all I comma j, that means this last term is not there. Okay, this implies your rho AB is a product state. It's a product state. Product state means separable state. So if you want to have an entanglement, then the entanglement actually contains in this last term. So if you have entanglement, then at least some of these Tijs have to be non-zero. And that is the reason why we say this matrix T, okay, which is basically the matrix of these Tijs, okay, this is called a correlation matrix. Correlation matrix. This is called a correlation matrix because this is where the correlations are built in. The correlations are in this matrix Tij. Okay. Now we want to ask a question that so the main question is something like this. Suppose, so let us say that if a mixed state rho AB is entangled. Or let us put it this way. So our question is something like this. How do we determine if a mixed composite state rho AB is entangled or separable? Okay. Now, as I told you here, if Tij is equal to 0, we can say it is not separable. But if all Tij is non-zero, or if some of the Tij is non-zero, that does not mean it is entangled. Okay, so it is necessary but not sufficient. So by just looking at that one, we will not be able to tell whether a given mixed state is entangled or not. It's a correlation matrix, no doubt, but not that every non-zero correlation matrix will be will give us an entanglement. Okay. So we require a criteria to determine if a mixed composite state is entangled or separable. Now, our previous criteria will not work because when you take a partial trace of rho AB, since rho AB is mixed, all its partial traces will also be mixed. So we cannot use earlier when we had pure states, when you take partial trace, if you get mixed state, then you are saying that initial state is entangled. Correct? So rho AB pure entangled means rho A, which is equal to trace over B of rho AB, is mixed. So there is a kind of a well-determined connection like this. If this is pure but not entangled, then this is not mixed. Okay, so that means rho AB pure separable. That means rho A, which is equal to trace over B of rho AB, is pure. So this is what we have discussed earlier, that for a pure state, you have a very, very well-determined signature in terms of its partial trace. But if rho AB is mixed, okay, so if rho AB is mixed, this implies rho A is always mixed. Mixed. Okay. So we cannot say just because rho A is mixed, rho AB is entangled or not. So this signature will not be, it cannot be used. Okay. Now there is uh, another operation that uh, we define here in order to tell this one. So this is something called uh, positivity under partial transpose. Positivity under partial transpose criterion. Is also called Perez-Horodecki criterion, because this criterion was initially proposed by Perez and then later Horodecki has proved many things. It is also called as PPT criterion. Okay. First, I will tell you what this criterion is, and then I will tell you the limitations of this, limited applicability of this criterion. Now, let's say that we have a row. Okay. So now what? So first we have to define this operation called partial transpose. So first we understand how to take this partial transpose. Partial transpose. You know, if you have a matrix, how to take a transpose. So let us say that my row is something like this. So I divide this. This will be a 4 by 4 matrix. I will divide this into two in a block of 3 by 3 matrix. So let us call this as B00, B01, B10, B11, where each one of them, B00, or let me simply call it as Bij, will be basically you will have row 00 ij, row 01 ij, row 10 ij, row 11 ij. So there are elements like this. So these are like blocks. Okay. Now you can take partial transpose over subsystems. So let us define rho prime to be partial transpose over A of rho. That is given by you take transpose of this one, B01 transpose, B10 transpose, and B11. Okay, that is you take the transpose of each of this block. This is partial transpose over A. On the other hand, you can also take partial transpose over B of this row, which is essentially block-wise transpose. So that means I'm going to have B00 and B10, B01, and B11. Okay, so now you can see that I have made this block. This block will go here and this block will come here. This block-wise transpose. This is So transpose, considering the block as an element. Here, every block is transposed. This is how the partial transpose is constructed. Now, the theorem that is proved by Hierarchy and is the following. So the theorem says that for bipartite systems of dimensions 2 cross 2, that means 2 qubits, and 2 cross 3, that means a qubit qubit system. Okay, for 2 cross 2 and 2 cross 3 system, partial transpose of a state rho is positive if and only if rho is separable. That means when you do a partial transpose over one of the subsystems, and if that turns out after you do partial transpose, then if it also turns out to be a positive operator, that means rho is separable. Now, this if and only if is true only for these two systems, 2 cross 2 and 2 cross 2. For other dimensions, this is necessary but not sufficient. That means if it is positive, we cannot say that it is separable. If it is separable, it is positive. But if it is positive, we cannot say that it is separable. Okay, so this is the theorem which was proved by Hierarchy, and this is what is used to understand if a given mixed state is entangled or not. Now, let me just illustrate this with a very important state which was discovered or proposed by Werner. This will talk about that state called Werner state. So this is introduced by Werner in 1989. So he introduced this state. It's a very clever construction. Okay, so this is a mixed state. So this state is constructed. So this state is constructed as a convex combination. Convex combination is another name for what is called probabilistic mixture. Probabilistic mixture of maximally entangled pure state, maximally entangled pure state, and maximally mixed separable state. Okay. Now, if you see this construction, it's a very clever construction in the sense here entanglement, pure state means pure. There is nothing like maximum pure or anything. Pure state is just pure. Okay, there is no gradation in the purity. So you take a pure state and then increase the entanglement to maximum level. That is one state. Then separable is separable. There is nothing like gradation in separable. Okay, you take a separable state and increase the mixing. So maximally mixed separable state. So now you take these two things and then add them. I mean, basically you convex combine them or take a probability mixture of that. Okay, so this is what we call as rho W. Let me call it as rho W because it is in because it is called Werner state. So rho W is equal to, so let us say that I have 1 minus P times I by 4. Okay, I by 4 is basically the identity matrix by 4, 4 by 4 matrix identity by 4. If you want, I can write it as I4 by 4 plus P times, I'm going to write one of these Bell states. So 5 plus and 5 plus. That is the maximally entangled Bell states, where this 5 plus is given by 1 over root 2 times 0, 0 plus 1, 1. Okay, we have used this state. So if you see, so this is maximally entangled pure state. Whereas I4 by 4, what about I4 by 4? I4 by 4 is maximally mixed separable state. Okay, because I could have written I4 by 4 as I2 by 2 cross I2 by 2.
So how it is you're calling it as mixed states? Yes? Separable state understood. How is this mixed state?
I showed you here in the block sphere case that identity by 2 is the maximally mixed case. That is the origin. Now that can be generalized to any particular dimension. So if you have a d-dimensional system, then 1 by d into identity operator, a d cross d identity operator will be the maximally mixed state.
So what I'm asking is there any proof to tell them that identity by 2 is the maximally mixed state? Is there any proof for that?
See, the point is that whenever you have an identity, that means basically it is the probability for each one of the pure states in terms of which you can decompose is same. That means it is like equal probability, and equal probability is the maximally mixed state. You cannot have a more mixing than that. Okay, so it is just a definition of a maximally mixed state.
Okay.
So
Okay.
from here, the postulate of equal apparent probability comes from it.
Yeah. So if you want to mathematically represent an equal a priori probability using a density matrix, that will be identity matrix.
Identity by the dimension.
Correct.
Okay, sir.
Okay, so now we have this, and this parameter p is between 0 and 1. Because if p is equal to 0, for example, then that is maximally mixed separable state, and if p is equal to 1, then that is maximally entangled pure state. So now the question that we are interested in asking, of course, there are many interesting questions which Werner has asked in that paper of 1989. But we will not ask all those questions today. But one of the interesting questions that we would ask is the following. So we know that for p is equal to 0, rho w is separable. Okay, rho w is separable. And also we know that for p is equal to 1, rho w is maximally entangled. Maximally entangled. Now, what can we say about rho w for some p between 0 and 1, other than 0 and 1, but between 0 and 1. Now the point is something like this. Suppose p is very small. That means there is a small component of entangled state that is there. So is that enough to make the entire state entangled? Okay, sometimes we say that no, if you have a pot full of milk and one drop of poison, the whole thing becomes poison. So is it something like that? P is very small, but then it will make the entire state entangled. Or is there some critical value of P only above which rho W becomes entangled? Okay, so we would like to ask a question as to for what values of P is rho W entangled. Okay, so for what values of P in 0, 1 is rho W entangled. Okay, so this is the question that we would be interested in asking this question. Now, since rho W is a mixed state, then we have to use this PPT criteria to answer that question. So let us try um, answer this question. For that, we have to write a matrix form of this. So that is your rho W is equal to, so we have this 1 minus P by 4, 0, 0, 0, 0, 1 minus P by 4, 0, 0, 0, 0, 1 minus P by 4, 0, 0, 0, 0, 1 minus P by 4. This is the first matrix, 1 minus P times I by 4. Plus the second matrix is, as you know, that your 5 plus, so remember your 5 plus is 1 by 2 times 1, 0, 0, 1. So 5 plus will be P by 2, 0, 0, P by 2, 0, 0, 0, 0, 0, 0, 0, 0, p by 2, 0, 0. Okay, so this is our matrix. So this we can write it as a 4 by 4 matrix of this type. So this is 1 minus p by 4 plus p by 2. So that will be 1 plus p by 4, 0, 0, p by 2, and 0, 1 minus p by 4, 0, 0, and 0, 0, 1 minus p by 4, 0, p by 2, 0, 0, 1 plus p. I can see that 1 plus p by 4, 1 minus p by 4, 1 minus 1 plus, the trace of this matrix is 1. So that is what is required. Now we want to understand whether this is entangled or not. So for that, we can try to look at a partial transpose operation. So let us try to take, we'll call this rho prime, which is equal to partial transpose over A of this rho. So that means what we have to actually consider these blocks. It is blocks and then transpose each block. So the first block, there is no change. So the rho prime is equal to, this will be 1 plus p by 4, 0, 0, 1 minus p by 4. This block is as such. Now I have to transpose this block. Okay, so that is 0, 0, p by 2, 0. And this one is 0, p by 2, 0, 0. And this block doesn't change. 1 minus p by 4, 0, 0, 1 plus 0. Now we have to ask a question whether this particular matrix is positive or not. Okay, so we have to verify. We have to check. We have to check if rho prime is positive. Okay, so for that, what we will do is we will try to look at this criteria: delta 1, delta 2, delta 3, and then this whole determinant. So 1 plus p by 4, that is our delta 1. Delta 1 is equal to 1 plus p by 4 is always positive because p is greater than 0. Is always positive, so there is no problem. Now second, delta 2. Let's look at delta 2. Delta 2 is 1 minus p square by 4. 1 minus p square by 4. Since p is less than 1, p square is less than 1, this is also always positive. Okay, since p is less than 1. And this is positive since p is greater than 0. Okay, these things are done. Now you have, so now you have to take 3 by 3 determinant. So the 3 by 3 determinant is, that is your delta 3 is 1 plus p by 4 into 1 minus p the whole square by 16 minus p square by 4. 1 minus p square by 16, 1 minus p whole square by 16 minus p square by 4. So I can write this as 1 plus p by, I can pull out a 4 and write a 16 here, into 1 minus p the whole square divided by 4 minus p square. So that is equal to 1 plus p by 16 into, I have 1 plus p square minus 2p. Maybe I can also pull out that 4 here, minus 4p square. Okay. So that is basically, that is equal to 1 plus p divided by 64 into 1 minus 2p minus 3p. Right? So yeah. So so this is anyway, since p is greater than 0, this quantity is anyway positive.
Sir, instead of doing it this big, why can't we use the other condition, sir? That x bar t mx greater than 0. It will be like a single step also.
No, that is not single step, because that you have to check for all x, and there are infinitely many x. That can never be used as a calculational criteria. That can be used as a definition, because you cannot check for all x, right?
Yes, sir. Yes.
So I think we should probably do this slightly differently. Okay, so let us do it like this. So I want to say that since p is greater than 0, this is always positive. Okay, so we require to only show that this is positive. Okay, so I can pull out also this 4 here and then put 4 here. So I have 1 minus p the whole square. Okay, this implies 1 minus p the whole square minus 2p the whole square. So this is what I have. Okay, so this is my delta 3. Okay, so that is equal to, I can write this as 1 minus p plus 2p into 1 minus p minus 2. Okay, that is equal to 1 plus p into 1 minus 3p. Okay, so 1 plus p is this is positive. This is positive. So this has to be positive. That means delta 3 has to be greater than 0 or greater than or equal to 0, implies this 1 minus 3p has to be greater than or equal to 0. That tells you p should be less than or equal to 1 by 3. Now this is the condition, and the full determinant will be anyway, if you take the determinant of this 3 by 3 blocks, that has to be multiplied by 1 plus p by 3, which means 1 plus p by 3 is positive, so full determinant will always be positive. Okay, so we get a condition that p has to be less than or equal to 1 by 3. So that means if you look at the parameter space, so let's say this is your p 0 to 1, this is your p, and there is some 1 by 3 here, and in this region, rho w is separable. Whereas in this region, that is p greater than 1 by 3, rho w is entangled. Okay. So rho w is separable in the region 0 less than or equal to p. So that is 0 less than or equal to p less than or equal to 1 by 3. And this is entangled 1 by 3 less than p less than or equal to 1. So in this region, it is entangled. So like this, we can use this positivity under partial transpose criterion to, uh, to talk about the separability or entanglement of a mixed state. Okay, so this is an example of a mixed state. So I wanted to show this example because uh, this is a very interesting state. It has many interesting properties, and people, especially in theory, people use this state very often. So I thought I'll introduce this state right in as an example of how to measure entanglement using PPT criteria. Uh, uh, no. See, what I'm saying, determinant, see, determinant of the whole matrix, determinant of rho prime is basically 1 plus p by 4 into delta 3. Okay, so this is positive, delta 3 is positive because 1 plus p by 4 is positive. Yeah, so it's not going to change the result. So p less than or equal to 1 by 3 is the condition for the separability. Okay, so now let me tell you that a similar condition. Okay, so this condition, that is PPT criterion, for separability is both necessary and sufficient. Necessary and sufficient only for 2 cross 2 and 2 cross 3 bipartite and there is um, for higher dimension systems, that is for other bipartite systems, okay, for other bipartite systems, it is necessary but not sufficient. So we don't know, that is, having a condition that is both necessary and sufficient for a general bipartite system is still an open question. We don't have a criterion or an equivalent criterion which is both necessary and sufficient for a general bipartite system. For example, if you take 3 cross 3 systems, 2 Qubit systems, this is necessary but not sufficient. So so this is about this Perez-Horodaky or PPT criterion, which is very useful as far as 2 qubit and qubit systems are concerned, because that will tell you what is whether a state is entangled or not. And based on this entanglement criteria, you can also define certain measures of entanglement. Okay, so that is also possible. We will define those measures in our next class. So we can also define a measure. There's something called negativity. If, for example, this partial transpose is negative, then it will have negative eigenvalues. Now, based on how much is the eigenvalue, the negative eigenvalue, you can make an estimate of how much entanglement is there. So negativity is one entanglement measure based on the eigenvalues of the partial transposed matrix of a density matrix. So this is one criteria. But interestingly, I think there is another situation in which this is this criterion works, that is in infinite dimensional. Suppose if you have, there are certain states called Gaussian states. So if you have infinite dimensional continuous variable systems, then this PPT criterion once again is both necessary and sufficient. And of course, you have to learn something called Wigner function formalism in order to understand how to calculate partial transpose of a density matrix in a continuous variable. Okay, so we will try to see if we can get some time, then we will try to discuss that formalism. But I just want to tell you at this moment, other than 2 cross 2, 2 cross 3, there is an infinite dimensional Gaussian states for which PPT criterion is both necessary and sufficient. Okay, so I will stop here. If you have some questions, you can.
Sir, but I read in a book that for Werner State, the criterion is P is greater than or equal to 1/2, but we are given a 1/3.
What did you say?
P value gets given as 1/2, sir, in some books.
Yeah, so I do not know which book, but there is no reason to worry because I have defined this in this way, but some people try to define it maybe differently. But you have to see if they have defined like what I have defined, then this is correct. There is nothing to doubt here because I have shown it in front of your eyes. There is no magic. Everything is proved.
Yes, sir, yes, that's true. But I was confused because I thought it's a general criterion. Anyone will follow the same thing, but I think there they have defined differently.
Yeah, if they have defined with a different notation or with a different way, then it can change. But you have to see how they have defined it.
Sir, you have mentioned that Gaussian states are like continuous basis, infinite dimensional continuous basis.
Yeah.
Is this like position representation, momentum representation, sir?
Yeah, so if you want to talk about those states, then you have to choose one of those representations. You can either represent it in position basis or the momentum basis.
So are those bases are those bases part of Hilbert space, sir? Because in Hilbert space we have the square integrability condition.
Correct.
But position basis and momentum basis, they don't satisfy the condition.
Well, that I think you are talking about normalizability problem, right? Because of the normalizability problem. But that is, you can overcome that by something called some extended normalization. If you allow that Dirac delta function as a part of your vector space.
No, I'm saying that they don't actually satisfy the square integrability condition. Like,
I agree.
But you are talking about the inner product, no?
Correct.
Inner product is like instead of Kronecker delta, use Dirac delta.
No, what I'm trying to say is that if you consider let's say e power ikx,
Yes, sir.
okay, then you are saying that e power ikx is diverging. Is diverging when you take square integrability of the function. Okay, but suppose if I write that e power ikx into e power minus ikx prime dk as some delta of x minus x prime, and I do not consider that as infinity, that is allow for the delta function divergence, then I can use that.
Okay, sir.
But I agree that it is not strictly a square integrable function.
Because in Zetli book, they have mentioned that it's not a part of Hilbert space, but they form a basis of Hilbert space. So I was confused.
Yeah. So that is essentially it is used with this normalization criterion. It's called extended normalization criterion.
Okay, so and so sometimes people use box normalization.
Correct. That is when physically you know that there is some volume in which particle is there or a length in which particle is confined, then you can use box normalization. And probably even if you want to relax it later and you take at the final result L tending to infinity or V tending to infinity, that limit.
Okay, sir. Thank you.
Yeah. Okay, so if there are no questions, then we can.
Hello, sir.
Yes.
Sir, I just wanted to inform you that my email was not added to the email list.
Okay, so your email has changed, is it recently?
No, sir, it hasn't been added from the start. I haven't been receiving any notifications.
So your email was not that same thing that is there in your SAM. I think I have taken your list from that SAM.
No, sir, I think I registered late, so my email wasn't added.
Okay, so you recently sent me a mail, right? So I have to
Yes,
add
sir.
that email address. Okay.
Okay, sir.
Sir, one like unrelated question. Like I have recently seen a notice that from Pondicherry University that the entrance examinations is going to be held on the second and third week of June. But if someone has